Okay, so let's go back a little bit in time. And where I want to travel with you is essentially the early days of IoT and, more importantly, industrial IoT. So maybe few of you know that in 2008, we were the company supporting development such as Connected Boulevard in Nice. So in 2008, that was one of the earliest smart city in the world. And back then we were providing essentially the data connectivity framework for applications. In 2014, we were, along with Cisco and a few other companies, the team that established the first fog computing platform for the Barcelona smart city infrastructure. And so, in a way, we were there. We've done that, and if you was, it was laborious. It was complicated, and if I was to make a parallel, I would say that each time we had to do one of those projects, it was like Heracles 12 labors. Why so? Well, because we had to stitch several technologies together. We had sensors, embedded sensors, and you had to use one technology to get the data from that sensor. Then you would have to get this data somewhere. You had to use another technology. Then eventually this data had to be stored, and yet another technology. And then you have to retrieve to do computing, yet another technology. It was just a mess, okay? Complicated, frustrating, very hard to have an end-to-end semantics. And yeah. So I think, again, the Heracles 12 labors, it's a very good parallel of the pains we were feeling. And so another way of looking at this, it was really a chaos. But the other things that was kind of paradoxical, at least for me, is that it's like the frog in water that warms up. If you're used to something, it feels normal, okay? And it's only when you realize, and sometimes you never realize, okay, that there is another way, or that maybe you should look for another way, that you start realizing how the current way of doing things, it's kind of off, okay? And there was this kind of malaise, this kind of, no, this cannot be right. But we felt like, we were only seeing these challenges and these pains. And what is worse, if you think about it, most of the integrator, they live out of this mess, okay? So the technology provider would like to have a technology that works and makes it simple. Big system integrator live out of the mess that is created by this technology island. So it's very profitable for them. So anyway, we were trying to step back, but people were just not listening or not interested necessarily in looking at how we could structurally solve the problem, and everyone kept pushing the solution that they had, like trying to squeeze an elephant into a small door. So back in 2014-15, the key technologies that were considered as emerging, between quotes, were MQTT, DDS, especially in those domains. And again, I recall to those of you that don't know that MQTT was invented in 1996, and DDS, of which I was one of the guy that started the standard, dates back to 2003, 2004. So those technologies were at least 10 years old and were designed for different use cases and slightly different world. With that understanding, we said, look, especially, for if we take one example for DDS, we said, look, there are this kind of limitation. We would like to work around this kind of limitation. And back in 2015, we proposed some changes, some extensions to the DDS-ware protocol, okay? And those extensions were notably intended to address the challenges that there were with discovery, scaling discovery, the challenges that there were and that we had been facing and tried to address or work around to scale out geographically DDS, the challenges that there were with respect to wire overhead, because all of a sudden we needed also to deal with constrained networking protocols. And if you have 60, 70, or 80 bytes overhead per sample of data that you send, this is more than an MTU on some low-power networks. So just not possible, not doable. But in any case, in spite of our efforts, inertia, ossification, and vendor wanting to maintain their position prevailed. So at that point, we decided, okay, so there are really two choices. Either we resign and decide to just continue like this, or like, no way, we do something else. Who cares? And then we'll see what happens. And this is essentially what we did. So we decided to take up the challenge and design a new protocol that, while capitalizing from more than 20 years of experience that we had with distributed system, and the fact that we had been working since the very beginning with the transition from the system we were before, which were mostly high-performance distributed system used in aerospace and some other mission-critical application like air traffic control management, to IoT and industrial IoT. So to capitalize all of that and come up with a protocol that, first of all, could really unify data sharing from the cloud to the microcontroller. So that was the first challenge, which means being able to scale geographically and being able to scale up and down, meaning deliver good performance when you're running on high-end hardware and high-end networks. At the same time, use small resources, little resources on constrained hardware and constrained networks. And there are lots of protocol designs and consideration that you have to do under that. We won't be able maybe to cover all of those today, but we'll definitely have more information sharing, and some of our blogs on that Zenoh.io already cover some of those aspects. But that wasn't it, because as we set ourselves for this challenge, to make it even a little bit more interesting, we said, well, there is actually another problem that's been bothering us forever. And the problem is that you have location transparency for data in movement. So if you're moving data around and you use some pub/sub technology, location transparency essentially means that you do not need to care where the source of the data is. You really don't need to know. Typically, you express your interest in some data, a topic or whatever it is, and you receive it. As soon as data is stored, you lose that transparency. And that consequence poses several complications when, once again, you try to move to decentralized architecture and you need to have storages that are geo-distributed. How do you know where the data is stored? It gets very complicated. And so the ability of having transparency for data at rest as well as for data in motion, and having one framework that allows you to unify data at rest and data in motion, was for us kind of the holy grail, and one of the big problems that we were struggling and that we had to work around by stitching together technologies back then. So these were the premises and the condition under which eventually Zeno was started. And the result was a protocol that really put together the state-of-the-art pub/sub protocols, state-of-the-art NDN technologies, some named data networking protocols, to really come up with, as we will see, a very small and orthogonal set of abstractions that allow us to unify data in motion, data at rest, and actually computations, okay? And you will see that throughout the day also in the demonstrations. This protocol was designed in such a way that it can really scale, and we will see the numbers, from high-end hardware and networks to very constrained devices. So you will see numbers, you will see it in actions. So that's not just slideware, it's running software. And once again, location transparency, not only for data in motion, but also for data at rest, which was one of our key goal. And this idea of geo-distributed queries. So all of a sudden, I express the data I'm interested in, I issue a query, and it's Zeno that crawls the network to figure out how to get it. So the protocol was designed really to run anywhere. So written, by the way, in Rust for performance, safety, and security, and designed in such a way that it can run already on top of a data link. So what does that mean? That means that technically we do not need an IP network. We can do our own routing, and this is why Zeno has its routers. Those are soft routers. Obviously, we are not saying that we are here to replace IP, because we can run very, very well over an IP network. But the point is that in some instances, you cannot afford to run IP because of the overhead. And being able to run something that is more wire efficient than IP, it's convenient. In some instances, you need to bridge across networks that are non-IP. So our ability to run on top of a data link, on top of a network, or perhaps on top of a transport, and the transport could be IP as anything else, that's very powerful, okay? So As I mentioned, our core technology is developed in Rust, but obviously we provide language bindings for an array of programming languages, so Rust, C++, Python, Java, Kotlin, and so on and so forth. And yeah, as I mentioned before, very efficient web protocol. I'll give you some number going forward. Moving now to the abstraction. What are the abstractions at the foundation of Zeno? So Zeno deals with resources. What is a resource? A resource is nothing but a key value pair. Okay, something like home, kitchen, sensor, temp, and then 21.5 Celsius, and so on and so forth. So this is really what Zeno deals with. Then you can identify a set of resources by means of key expression. So a key expression looks something like home, kitchen, sensor, star. That would be all the sensor that I have in my kitchen, for instance, in my house. You can use double star to expand to as many nesting as you want. And there are some other things that you can use in key expression to actually select the set of keys or that you're interested in. There is another way of dealing with the resources, which is selectors. And a selector allows you essentially to identify a set of resources that not only matches a specific key, but also matches, right, or satisfy a predicate. So in this case, for instance, would be the CO2 greater than 12, allows you to do projection, okay, and perhaps allows you also to pass some properties. So in terms of abstraction, Zeno really builds on 3 network abstraction. In Zeno, you have publishers, which are spring of value. So a publisher, if you think about watery abstraction, is a source of values, okay, coming sparkling from somewhere. You have a subscriber, which is a sink for value of a given key expression. And then you have a queryable. So a queryable, again, is a network endpoint, and you have to think of a queryable like an oracle. So a queryable tells just, look, for anything you look that matches this set of this key expression, just come to me. And however it will answer to your query, you are not due to know. And we will see that, for instance, we can use this queryable abstraction to implement or to represent distributed computation, to represent distributed storages, and all of a sudden, you can, with just one primitive, as we will see, which is our query primitive, either trigger a distributed query or trigger distributed computation. And by how we do consolidation, right, you can either consolidate the result of the computation of the query, or consolidate the result of the computation to implement mechanisms that looks either like MapReduce or perhaps voting systems and so on and so forth. So 3 abstractions, okay, and again, another way of thinking about the queryable, if you continue with this water abstraction, is to look at it as like a well. A well is a place where you go with a saw to look for water, okay? And then what are our primitives? We have obviously primitives to sessions. During a session, we do lots of things. You have even the ability of negotiating the resolution of the sequence number, because obviously, as we target wildly different network, there isn't a sequence number resolution that can work well across a constrained network and perhaps a satellite link, right? On a local area network, on a personal area network, you want to have perhaps the smallest sequence number because you send sporadically data and you don't have lots of packet in flight. If using a satellite link, you really want to have lots of packet in flight, thus a bigger number resolution. Zeno allows you to do that, to optimize your communication depending on your network. Then there are primitives to declare and obviously undeclared network endpoint, like subscriber, publisher, and queryable. And there are the primitives, just 3 primitives, to operate on resources. So you can put resources that sets a value for a resource. You can pull a resource. A pooling of a resource essentially allows you to consume data for a subscription, and in this case is the infrastructure that makes sure that the data is cached as close as possible to you. This is very useful for a device that go under sleep. And then we have the get, and the get is nothing but the distributed query. So when you do a get, you provide a selector, and Zeno will do a set coverage, find the optimal place where to answer that query, route the query to those queryables, and then consolidate back the result. Zeno supports, or I would say rely upon another sub-protocol that we call the scouting protocol. The scouting protocol technically is not part of Zeno, it's used in order to bootstrap Zeno. And the scouting protocol leverages, or it's dependent on the underlying network technology. So the way in which we do scouting on an IP network, or the way in which we do scouting on Bluetooth, and so on and so forth, might be different, okay? And I think of scouting as a generalized bonjour. It's really a way to figure out who is around, find some anchor point, and from there, discover the topology of the network. So, as I mentioned before, you will be seeing today that Zeno runs on just about everything, and I know you will have more on the Zeno team presentation. And we support any topology. So this is quite unique compared to technology like MQTT, AMQP, or DDS. Because if you look at, if we compare to extreme, MQTT and DDS, MQTT supports only the hub and spoke architecture. And in DDS, you have peer-to-peer with full graph. So every node has to be able to reach any other node. In Zeno, we can do peer-to-peer over a click, which means a fully connected graph, or an arbitrary mesh. We can have brokered communication, and we can have routed communication. And by the way, even our peers are able to route communication for clients. Then is extensible. We will see this in action during the demo. And you can use its extensibility to integrate with third-party protocols. So we have already integration with DDS, integration with QTT is coming, integration with several data stores for implementing our storages, and so on and so forth. And if we look at performance, Zeno is capable of delivering, on high-end hardware, millions of messages per second. And if we look in terms of bandwidth, we are, well beyond typically 40 gigabit per second, when the iPerf on a similar network delivers around 50 gigabit per second. Okay, and that's obviously running on top of TCP/IP, just to make sure that we have apple-to-apple comparison with iPerf. In terms of latency, we have a latency of about 35 microseconds, working to reduce that. I mean, there were some, we are in some discussion with the async team to try to improve certain things that will allow us to further reduce the latency. And the wire overhead can be as small as 4 to 5 bytes. And in general, it's between 4 and 6 bytes. So if we try, and this is in a peer-to-peer scenario, if we try to put this into perspective, so suppose now we say, okay, fine, let's compare Zeno with MQTT. So let's put a router in between a publisher and a subscriber. How does it compare? Well, here you see the difference. On the same network, same programming language for the publisher and the subscriber, you see that Zeno delivers order of magnitudes more performance throughput than MQTT. While, as we'll see, being more wire efficient, as you see in the next diagram. So the next diagram is really how compared to other protocols that, especially in robotics, sometimes considered for dealing with constrained target, like XRC and MQTT, it provides more wire efficiency beyond providing better performance. And for what concerns performance, here you have a performance of microcontroller. Again, we will see the application of Zeno on several controllers later on today. But here you have a glimpse of the throughput that it provides across small ESP or perhaps ST32 board. So summing up and trying to go through some protocol highlights. So Zeno provides today a very wire, power, and memory efficient protocol, again, that you can use for connectivity from the data center to the microcontroller. It supports pub/sub, both in push and pull mode. In other terms, whenever you establish a subscription, a subscriber can tell, look, I want data to be pushed to me, or Zeno, please, as I'm a subscriber that perhaps has a duty cycle, just keep the data that is related to my subscription somewhere as close as possible to me, so that when I ask you, you'll get it. I'll get it in the most effective manner. And we also support distributed queries. Now, I've been talking about wire efficiency and 4 to 6 bytes overhead. And at the same time, you saw that we represent resources by keys. So the question is, how do the two adapt? Well, because a key can be arbitrarily long. So the reality is that over the wire, with data, we never send strings. So what we do, we always map strings within a session to small integers, usually single byte integers. Then obviously that depends on how many resources you have. But this is how we minimize our bandwidth. And the other important thing is that these integers, you never see them from an application perspective. The mapping is done automatically. And any necessary mapping to ensure that end-to-end, although one session may be assigned to resource 15 and on the other hand is 31, still communication happens. So all of that is done automatically, and you don't need to take your head with a global resource mappings. So we have support for, as we saw, peer-to-peer, as well as routed and broker communication, support for zero copy. We support ordered, reliable delivery and fragmentation. And as I mentioned before, the wear overhead is fairly small. So in summary, final thought, Zeno was redesigned ground up to deal with data management from the cloud to things, or in the cloud to things continuum. It unifies data in movement and data and delivers incredible performance. And as you saw, and you will continue to see today, it can run just on about anything, from high-end to very constrained hardware.